In this lecture, we talk about cyclic Galois groups. So a Galois extension is called cyclic if the corresponding Galois group is cyclic. So say you have the roots of this equation, xn minus 1. And so the roots of this equation, they form a cyclic group. 1, this zeta n, zeta square n, zeta n minus 1. You denote this group by mu n, and this is generated by this element here. So this is the primitive element which is generating this group. So this is a cyclic group, as you can see. So this is a cyclic group, and this group mu of n is contained in the units of this field. So the multiplicative group associated with the units of the field, which contains this primitive root of unity. So again, suppose you have a field and you just consider it as a group with only its units, and the group operation is multiplication, and this field contains zeta n, then this field obviously contains the subgroup generated by zeta n. So let K be this alpha adjoined with f, and this f already contains this primitive root of unity zeta n. So f already contains this zeta n. So where alpha is the root of this equation, so alpha, in fact, you set it up as alpha is equal to a to the power of 1 by n. So this polynomial splits like this: x minus alpha times zeta n 1, this, and so on. So this is the factorization of this polynomial. Now, so K is a Galois extension of f, and since it is a splitting field of this polynomial, f already contains zeta n. So the Galois group, which is this group, Galois group of K over f, and K you just have it by adjoining alpha, will just permute alpha, because zeta is already contained in the f, and the Galois group fixes element of f, so only alpha will be permuted. So the Galois group simply permutes alpha. So to see this, you can see it like this. So this f alpha is K, so Galois group of K over f. It takes the map sigma I, which sends alpha to alpha zeta n I, and this is in 1-to-1 correspondence with elements of our cyclic group. So you're taking this map, say alpha getting mapped to, so this alpha gets mapped to some root here. So it gets mapped to, say, root I. So this map you denote as sigma I. So this map, we are saying, is precisely in correspondence with this I. So now you can see that for every root you have a sigma. So this is identity map, this is sigma 1, which takes alpha to alpha zeta 1, then sigma 2, which takes alpha to this alpha zeta 2. So they are in 1-to-1 correspondence. So the only thing you need to check is that this is a well-defined homomorphism, which you can check easily, and this 1-to-1 correspondence will tell us that this Galois group is now cyclic, because this group mu of n is cyclic, generated by a single element, and this is obviously isomorphic to z over nz. So the only thing we need to worry about is injectivity is kind of clear, is surjectivity. So we don't want this alpha to the power of d should lie in n for some d less than n. So the point is this: so say if your d is less than n, and what is going on is you have sigma d of alpha, that is, you apply sigma d times to alpha. So by multiplicative property, this becomes sigma alpha d. Now if this alpha d ends up lying in f for d less than n, then obviously you cannot associate this zeta along with it, and then this surjectivity will kind of fail. So to prevent that, we make sure that alpha to the power of d does not lie in f for any d which divides n or d is less than n. So to wrap it up, what we have proven is this: so say K is equal to f alpha, where f already contains the primitive nth root of unity, and alpha to the power of n lies in f. So here you can say this is polynomial over f, so a obviously lies in f, which implies alpha to the power of n lies in f, and with no smaller power of alpha in f, so as to you can ensure surjectivity. This would imply that our extension, our Galois extension, which corresponds to our polynomial this extension is cyclic. So we have given a condition like this, which implies that the Galois extension would be cyclic. So we want to show that the statement is if and only if. So that is, we also have this direction. So if k over f is cyclic, we will have k of the form f alpha, where alpha to the power of n will lie in f, and f would contain the primitive nth root of unity. So to do this, we first need to talk about Lagrange resolvent. So let zeta be the primitive nth root of unity, and this zeta is already contained in the field f. And you fix some alpha in k, and your Galois group k over f is generated by sigma. So this Galois group is cyclic. It's a cyclic group. Now what we will show is that k is of the form f beta, where beta to the power of n is some a which lies in f. So this is what we are going to show. So therefore, we will have in the reverse direction. Instead of alpha, now we have beta here. So we are taking our extension is cyclic, so that means the Galois group is cyclic. So we're taking Galois group as cyclic, generated by a single element, and we want to show that this implies that k is of the form f. Instead of alpha, we're writing beta, and this beta would mean that this beta to the power of n should lie in f, just like here. So let us see this. So beta, you write it as alpha comma zeta. So this is the expression for Lagrange resolvent. So this is how Lagrange resolvent looks like, and then you apply sigma to it. You apply sigma here. You write zeta sigma alpha, zeta square sigma square alpha, zeta n minus 1 sigma n minus 1 alpha. Now you apply sigma again to this equation. So you apply sigma here, and then you apply sigma everywhere here. Now again, we are already saying that zeta is a primitive nth root of unity which is contained in the field f, and our Galois group fixes field f. So zeta is going to be fixed by, so zeta is fixed by our sigma. So notice that we are writing zeta as the primitive nth root. So it is fixed by sigma. So you apply sigma beta, you get sigma alpha here. The zeta comes out sigma square alpha all the way to sigma minus 1 alpha, because this is a cyclic group of order n. So sigma n is identity map. So now we simply take this zeta inverse outside. So this we take outside. So notice first that zeta inverse is equal to zeta n minus 1. You multiply both sides by zeta, you will get 1 here and zeta n here, and zeta n is anyway 1 because zeta is the primitive nth root of unity. So you take this zeta inverse outside. So this alpha we write right here, and this sigma alpha we write right here. We are introducing a zeta here, so zeta inverse times zeta will give you sigma alpha. So this you will make zeta square, and you keep the sigma square as such. Then you have zeta cube sigma cube, and this term we have already taken into account, but we have not taken into account the term before this. So the term before this was sigma n zeta n minus 2. So that n minus 2 now becomes n minus 1, because when you multiply it with zeta minus 1, you get zeta n minus 2 here. So this is what you get. But this is precisely what we started with. It's precisely this entire term here, and this we said was beta. So this entire thing we write as beta. So we have this equality now. Sigma acting on beta is precisely zeta inverse multiplied by beta. So now what if sigma acts on beta to the power of n? So this will be equal to this because of the multiplicative property of homomorphism. But then sigma acting on beta is this, so we write it right here. This is just an element, so it just comes in like this, but zeta to the power of minus n is 1. So you get beta n. So sigma fixes beta n. So it acts on beta n, it just spits out beta n. So sigma fixes beta n. Now, sigma is the element of the Galois group uh, of K, which fixes F. So therefore beta n lies in F, because sigma is the element of this Galois group and it is fixing F. Now recall that in the lecture on linear independence of characters, we showed that there is a linear independence of automorphisms, 1 sigma all the way to sigma n minus 1. So if these are linearly independent, we can choose an element beta which is non-zero here. So you can choose some beta which is non-zero. So we do have a non-zero beta, because you can choose these alphas in such a way that you get a non-zero beta, simply because our automorphisms are linearly independent. So you have a non-zero beta which satisfies the Lagrange resolvent. And so this sigma I of beta, this is precisely zeta minus I beta, because application of sigma on beta just multiplies beta with this zeta inverse. You apply sigma to it again, that is, you get sigma square of beta. On this side you get sigma square acting on beta, and this side you have to again multiply it with zeta inverse, and this will give you zeta minus 2 beta. So you apply it I times, you get this. So this sigma to the power of I, this does not fix beta for any I less than n. So you keep on applying all of them, they will not fix beta, because each of these zeta to the power of minus I is unique for every I less than n. You can see them, all of them are unique till n minus 1, and when it is n it becomes 1. So for all I less than n, you keep this beta is a constant, but you are multiplying it with a different number, so you keep getting beta in a different mapping. So thus beta does not lie in a subfield of K, because it is not fixed at all. So therefore it has to be the case that this K is equal to f of beta. So this you can see, beta to the power of n lies in f. So you set beta to the power of n as a, which lies in f. So beta to the power of n lies in f, you set it as a. So, or you can say that now instead of f of beta, f a1 by n is equal to K. So we have been able to show this result. So K is f beta, beta to the power of n is a, which lies in f. And this the arrow implication is in this direction also.